Hello and welcome to the lecture series on railways, harbour, tunneling and airport for the subject code 18CV645, module 1, session 12b, numerical problems on super elevation and curves. So in this session we are going to cover some numerical problems based on super elevation and also the curves, lastly the references. So moving on to the statement of the first problem, if a 8-degree curve of a track diverges from a main curve which is having a 5-degree in the opposite direction in the layout of a BGR. Calculate the super elevation and the speed on the branch line if the maximum speed permitted on the main line is 45 kilometers per hour. So this is a statement of a problem. So we need to find out the super elevation based on the degree of a curves from the main line as well as the branch line for a BG track. So in the previous sessions we had explained how to calculate the super elevation from the standard formula based on the type of the track or the gauge we have been using it. Solution. So for this one, the equilibrium cant which is required for the given speed, that is 45 kilometers per hour, is calculated by using the standard equation. So that is E is equal to GV square by 127 R. So as I said it, so in the previous session also I had explained. So try to remember this standard equation. This is based on the given gauge length, the speed and the radius of the curve. So as it is going to be the broad gauge, so G value is going to be 1.76 meter. The speed it is been already given. To find out the radius we are going to be using the formula, that is 1720 divided by D. So where D is going to be the degree of a curve. So that is nothing but if you are going to be substituting 1720 divided by 5, the curve radius is going to be 344 meters. So just substitute all the numerical value in the super elevation formula. So that is E is equal to GV square by 127 R. So try to substitute all the numerical values. So we are going to be obtaining the super elevation or the equilibrium cant is going to be 77.77 mm or 7.77 centimeters. So for a BG track, the cant efficiency for the main line can be around 7.5 centimeter or 7.6 centimeters. We can use it, or it is going to be permitted. So in this case try to take value of 7.6 centimeter as a cant efficiency. Then cant on the main track is going to be whatever the numerical value it is going to be obtained from the equilibrium cant minus it is going to be the cant deficiency. So that numerical value if you are going to substitute, so it is going to be 0.17 centimeters. The cant to be provided on the branch line is going to be 0.17. So this 0.17 when it is going to be provided on the main line or branch line, it is going to be a negative value. Hence the numerical value is going to be written in the negative, and that numerical value is going to be called as a negative cant. So by using the cant deficiency, so if you are interested we can write the cant deficiency as the C of a D. So usually we represent it as cant deficiency. So this cant deficiency is going to be the 7.6 centimeter which is permissible. So what could be the cant to be provided on the branch line is nothing but, so cant deficiency and going to be the negative cant which is going to be provided on the line, it is going to be 7.43 centimeter. So this 7.43 centimeter is going to be provided on the branch line. So hence the permissible speed which is going to be operating for a branch line is going to be, once again reuse the same equation, that is going to be GV square by 127 R or 1.27 R depending upon the meters or centimeters value. So just to substitute here. So if you are interested you can find out this is going to be for the branch line. So whatever the value we are obtained, that is going to be the super elevation or the cant efficiency for the branch line. So the gauge is going to be once again the same thing. So fixed value. So R is going to be for 80 degree of a curve. So just to substitute in the standard formula, that is going to be 1720 divided by degree of a curve. So R is going to be 215 meter. Just substitute the value, and the end value after substituting in this standard formula, the speed is going to be 34.79 kilometer per hour. So this is a theoretical speed on a branch, or otherwise we can say 35 kilometers per hour we can allow for a branch line for the given condition of a 8 degree curve diverging from a main line with 5 degrees. So this is the standard type of problems to calculate the speed and also the super elevation for the given condition. So moving on to the next type of a problem. So the statement of this problem is like this. So what is the equilibrium cant on a 2 degree curve on a broad gauge if 15 trains and 10 trains, 5 trains and 2 trains are running at different speeds of 50 kilometers per hour, 60 kilometers per hour, 70 kilometers per hour and 80 kilometers per hour respectively. Say for example in a BG track or a broad gauge railway yard. So different trains are moving at different speeds and their numbers are given. For this case, how you are going to find out the equilibrium cant for a given 2 degree of the curve. So the first step for this one, as usual, we need to find out the radius. So in this case, radius is going to be 2 degree curve. So that is 1720 divided by d. So that is a radius. The same formula we are been using here. So radius is going to be 860 meters. So this is going to be a weighted average because different trains are moving. So depending upon how many number of trains we are going to be using, so that is going to be an arithmetic mean we are going to be using it. So that is for the speed of a one, how many number of a trains. So similarly, so different speeds then their numbers. Say in this case, so 50 numbers of trains are moving at 50 kilometers per hour. Similarly, 10 trains are moving at 60 kilometers per hour. Similarly, for the rest of the speed, just substitute in the formula and the number of trains. So we are going to be obtaining, and weighted average speed is going to be 58.13 kilometers per hour. So try to substitute this value in the standard formula for calculating the equilibrium cant, that is E is equal to GV square by 127R. So as we know, it is going to be a broad gauge, G is 1.676 and speed. So the speed is just we have found from the weighted average, it is 58.13 kilometers per hour, and similarly 127 it is standard, and radius of the curve is going to be just open here. So that is going to be 860. So by substituting all the numerical in this, so it is going to be 5.19 centimeter. So this is the equilibrium cant for a given set of parameters. So this is another type. Moving on to the next type of a problem statement. Calculate the super elevation and maximum permissible speed for a 2 degree broad gauge when transition curve on a high speed route with a maximum sanction speed is going to be 110 kilometers per hour. The speed of the calculating the equilibrium super elevation is as decided by the chief engineer is 80 kilometers per hour, and booked speed for the goods is going to be 50 kilometers per hour. So in this type of a problem, so try to analyze the equilibrium cant or the super elevation based on the sanction speed of 110 and also 80 kilometers per hour, which is being decided from the chief engineer. So solution for this problem. So the step 1, that is the same thing. First we need to find out what could be the radius for the given set of numerical. So radius is once again, so it is 1750 divided by 2, it is going to be 875 meters of a radius. So for the cant, if you are going to be using it for a design speed of 110, So for this 110, it is going to be GV square by 127 R. So G, it is going to be 1750, and the speed is going to be 110. Radius, it just now find it is 875. So for a speed of 110 kilometers per hour, so the cant is going to be 190.6 mm. Similarly, if the lowest speed for goods, it is going to be 50 kilometers per hour. So just substitute the 50 kilometers in the same standard formula. So we are going to be ending with 39.4 mm. So by adding all, we are going to be getting a cant excess. So that is for all the two type, that is given for 50, and this is for cant equilibrium of 75 mm for the broad gauge. The total cant excess is going to be summation of these two, it is going to be 114.40 mm. So as we are been operating at 80 kilometers per hour, so just once again use the same formula and resubstitute it, and we are going to be obtaining the for the 80 kilometers of a speed, the cant to be provided is 100.8 mm. So we are being concerned about the lowest value which are going to be taken into consideration. So one is with respect to the design speed of 110 kilometers per hour. So another numerical value what we are obtaining is 50 kilometers per hour. So then according to the restriction speed, it is going to be 80 kilometers per hour. So among these three, which one is going to be the least value? So that cant is going to be concerned. So in this case, first value is going to be 190.6, another is 114, and last one is going to be 100.8. So we are going to be concerned the least value. So then for calculation, so 100.8 or say it is going to be 100 mm is adapted to get back what is the actual cant to be provided. So as we know that for a broad gauge track, so all cant deficiency is going to be 75 mm. Hence the same thing we are been adopting here. So that is going to be 100 mm of a cant, that is the actual cant deficiency of a 75 mm. So to know what is going to be the operating speed, we are been using the standard formula V is equal to 0.27 multiplied by square root of cant actual plus of cant deficiency multiplied by the radius of the curve. So just to substitute here, as it is a 0.27 is a constant, square root of 100, that is a actual cant we are been providing, cant deficiency of 75 mm. So that is for a broad gauge track, multiplied by the curve radius of 875 mm. So then we are been obtaining the value. So it is 110.1 or say approximately 110 kilometers per hour it is can be provided. So that is going to satisfy all the requirements of different speeds. So this is another type of problem, you can expect it in the examination. So next type of a problem is based on the transition curve and offset, or to draw a curve according to the given statement. So in this problem, find out the length of a transition curve for a broad gauge track which is having a 4 degree of a curve and a cant of 12 centimeter. The maximum permissible speed on the curve is 85 km per hour. Draw the offset at every 15 meters. So this is the statement of a problem. So we need to find out length of transition curve first. So length of transition curve is going to be found by 3 criteria. So as I explained in the previous session. So one is based on the arbitrary gradient. So we are been assuming a arbitrary gradient for all the type of calculation of transition curve is going to be 1 in 720. So where we are going to be finding the E, that is going to be the super elevation or the actual super elevation. So in this case they had been provided as a 12 centimeter. So first formula, that is based on arbitrary gradient, the formula is L is equal to 7.20 multiplied by E. So length of curve is going to be 86.4 meters. So some of the authors will write length of transition curve as a LS, so it's no problem. So next is going to be based on rate of change of cant deficiency. So for that we are using a formula L is equal to 0.073. So cant or cant deficiency multiplied by what is going to be the maximum allowable speed we have been operating on the particular network. So just to substitute in the formula, L is equal to 0.073 multiplied by of 7.6 centimeters, and the maximum speed is 85 kilometer. So based on that one, the length of curve is going to be 47.16 meters, and last is going to be based on rate of change of super elevation. So based on rate of change of super elevation, so the same formula L is equal to 0.073 multiplied by the super elevation and the maximum speed. So just substituting the numerical in this formula, so that is L is equal to 0.073 multiplied by 12 and 85. So length is going to be 74.6 meters. So just look at the three different value based on the arbitrary gradient, length is going to be 86 meter. So based on the change of candidate efficiency, it is 47. Then the length based on the change of super elevation is going to be 74.46 meter. So by considering the highest numerical value, say that is going to be 86.4 meter. So or otherwise in multiples of 10 meter, approximately we can provide a 90 meter is going to be a length of transition curve. So we obtained what is the length of transition curve. So now we need to find out the offset at every 15 meter according to the statement. So as we know that we are going to be using a transition curve of a cubic parabola. So in the previous sessions also I had explained what could be the ideal cubic parabolic equation. So where y is equal to c of a x cube, where c is going to be a constant. So that is going to be obtained by the formula 1 over 6 multiplied by the radius of a curve, then L is going to be length of transition curve. So as we know that the same thing for the given set of condition, R is going to be the radius, where for the 4 degree of a curve the radius obtained is going to be 430 meter. So just substitute in this formula. So we are going to be obtaining the standard coefficient or the constant c is equal to 1 over 23 and 2200. So that is a constant. So next moving on to offset at every 15 meter. Hence, so first offset at 15 meter, that is a y is equal to 15. So then it is going to be x cube, that is already c value is obtained. So just to substitute the c value here, so multiplied by 100. So that is going to give you 1.15 centimeter is going to be the offset for 15 meters. So similarly, just substitute for the 30 meter. So the same equation y is equal to c of x cube, just substitute, and we are going to be getting 11.65 centimeter. So on till we are going to be ending with what is going to be the length of transition. So in this case it is a 90 meter. So up to 90 meter we need to find out the offset point. So similarly for 45 meters it is going to be 39.24 centimeter. Similarly for 60 it is 93.02, and for 75 meters of offset it is going to be 181.7, and at the end, that is at a 90 meter, it is 313.95 centimeter is going to be the offset line. So if you are interested, so that is the usual practice. So when we are going to be providing a curve from a straight line, say for example the straight line, and it is going to be a transition curve. So some amount of shift we are going to be providing. So that shift is going to be obtained by the standard formula L square, that is a length of a transition curve divided by 24 times of the radius. So just a substitute. So the shift is going to be 0.78 meters. So for better understanding, go for this sketch and we will know what is going to be the things we had calculated. So as I explained, so this is going to be the straight line or a straight track, it is coming over here. So at this zero chainage, actually our curve is going to be starting. So based on the offset, that is at a 15 meter, so that 15 meter is going to be around 1.15 centimeter here. So that is a 1.15 centimeter gap we are going to be providing from this shift of 15 centimeter. Similarly for 30 centimeter here, 45 centimeter, 60 centimeter and 75 centimeter. So overall we are been providing a shift of S. So this shift is going to be based on the calculation, it is 0.78 meters. So this 0.78 meters we are going to be providing as a shift to start our curve. So our length of transition curve is going to be 90 meters. So that is going to be provided. So likewise we are going to be providing offset point for the given condition, and for this we are going to be having a radius of 430 meters. So as a degree of curve is going to be, I think 4 degree. So this is how setting out of transition curve is going to be taken care from the given set of condition. So with this note we are going to end the session. So for references, the same standard textbook, Saxena, Subhash and Satyapal Arora and etc. are going to be referred to prepare this session. Thank you.